It's live.
Right. A little bit better, not much. Okay. All right.
Is there any way to orient the thing?
It's really annoying, but I'm not sure if we can fix it because the screen is what
Yeah,
is
the screen is
wrong.
tilted.
Oh, the screen's tilted. Yeah. I feel like someone's OCD would be like,
Like, if you untilt the screen, but I
You're open up Pandora's box right there.
don't think we have a nice enough screen to get it to.
oh, he's gonna weight it. Engineering.
That's going to be way too much.
Oh.
No, maybe not.
You have another back.
How about this? If you twist the screen slightly, it will even up.
Here.
At least the top of this will be. Look at that.
Maybe exactly 1.2 pounds.
That's better.
Yeah, just stand there.
This can't be on.
All right, everybody, welcome to the December edition of Orlando Python, or as it is otherwise known, OPUG. Today we have a presentation from deep learning from our friends from SiteHound. So they work on software that can actually like track you as you're on video and photos and things like that. And we have Enrique and Afshin today to tell us a little bit more about what they do at SiteHound and theory of deep learning in general.
Thank you. So as you mentioned, I'm Enrique and this is Afshin. We both went to UCF for grad school. I went there from undergrad through grad school, so it was kind of an 11-year journey. And I'm from Orlando. I guess to give a little more background, I graduated from UCF in 2014, Afshin this year in May. And I've been at SiteHound ever since, so 2.5 years now. And he interned with us last year and then got hired this summer. And our background is more in computer vision, so it's anything that's image or video related. So we've done everything from detecting objects or people or faces and images, tracking those things in video, action recognition. So that's, our big thing at UCF was being able to recognize these little micro actions. So like shooting a basketball, we had like a big sports database. So, and they kept growing it into more and more actions. And we have a pretty big research group at UCF for computer vision. There's about, at any given time, there's 20 to 30 of us in that one lab, and now they have 3 professors, and it's growing. But that's kind of our specialty. And so when we kind of approach deep learning, we'll be speaking about it from that direction. But all of these things are applicable to all the other things. Also, I noticed from the meetup, the page that there's like people of all there was even one guy that hasn't used Python before. So on the page, I don't know if he actually got here, but so we won't be talking too much about Python. We'll have some examples at the end, but we'll be giving kind of the high level of deep learning and then some details that hopefully don't lose you. And if you do, feel free to interrupt us and ask questions. But our goal is that you can at least have some vague idea of how it works, so that if you ever want to go look at it or as you're reading other things, it's not completely foreign and you just kind of run away scared.
Just one question before is that has anyone touched deep learning libraries before or played around with it?
And machine learning in general, like learning in general.
Okay.
So we did a machine learning talk 2 months ago on an intro, so the people who were there for that will have some idea.
So we'll be kind of relating this stuff to just classic deep learning, and then as we go forward, because classic machine learning, because deep learning is really old, but it's kind of gotten its modern flavor since 2011. So still, this new wave of deep learning is still in its infancy. So we'll just jump right into it. So what is machine learning? So as you guys already, probably most of you know, is that it's just this generic algorithm that you'd be able to take anything as input. It's going to learn that input and then give you, whenever you get something new, you want it to give you the correct output, right? So in the case of email, you might have an email that you receive, and if the title you have Viagra, you want to be able to say, run it through your algorithm and tell you if it's spam or not. So, in the early days, you might have just had more of a rule-based thing that would have been your machine learning, like if Viagra and the title spam, right? But that's gotten more sophisticated over time, and kind of computer vision, a classic algorithm has been digit classification, and so you would take these as images in whatever handwriting that you get and be able to output what the computer would recognize as an actual number, and then we could use that for other things. Now, this whole idea of machine learning came from the goal of artificial intelligence. So, the goal was to make robots and that could think and do things on their own, and we end up with this iRobot. But we're working our way there. This is kind of like a big thing in the computer vision community because it's kind of one of those first products that people have been able to actually use. But kind of like in the machine learning community, there's always been this dichotomy, like these two different views. So you have your more neuroscience inspired, which is kind of where this deep learning comes from, and the idea is that we want to model the human brain, that kind of do it like humans do it. And as we know, that's a lot harder said. It's easier said than done. So, but the main thing is that it's able to learn from examples, and it does true learning. Whereas kind of this classical symbolic AI was more about this rule-based architecture that I talked about earlier. And the problem here is that it can't learn from other experiences or other examples. And so it actually, when it's faced with new things, it kind of handles those very awkwardly, as we've seen with the iRobot. If you kind of see it get stuck in a corner, it just kind of goes back and forth and does back and forth and doesn't know what to do. So it's not really learning as much as it could. So we can kind of split this into several areas, but we're the two that we'll be talking about as we go along is going to be our supervised learning and our unsupervised learning. In supervised learning, the idea is that given an input, we have a bunch of labels. So we want to, given this input, what is this? And we have these labeled examples. So we'd have a bunch of examples of cars and motorcycles, and then we would tell our algorithm, whenever we give you a new car, label it, tell us what it is. And so this is kind of what most machine learning kind of focuses on. Now, an unsupervised is that you just give it a bunch of data, and then it would try to learn something from it, right? And then kind of cluster it into its own categories without us telling them what it is. So you would hope that it'd be able to learn car and motorcycle from that on its own, even though it doesn't know what a car and motorcycle is, so it is just like group 1, group 2, and then when you give it a new example, it'd be able to put it into its category.
The reason they are important is that you not always can go and label things, because for computer, in order to learn, you need not 1 or 2 images. You can sometimes need millions of labeled data. So computer needs to need all variation of data types in order for it to learn. So annotating and labeling data in like that scale is very difficult sometimes. So there is this huge group of computer vision people that are just working on unsupervised learning or semi-supervised learning, in which you don't need all the data to be annotated. So that's why they're both relatively important. But most of the applications that we're going to be talking about is focused on supervised learning, which is basically what's been mostly used get it completely.
So kind of to give a little bit of historical background, because it's related to this deep learning stuff, is that the first learning machine was a perceptron, and it was basically just an array of motors that were all wired together. And why this is important is that it was the first kind of thing that, it was a first classifier. So it was the first thing that you would give it an input and it give you an output of what it is. And so the main idea was that it would take this character, you'd be able to you'd run a really simple feature extractor, and then you'd run it through this perceptron, and it would give you an output. And so this is kind of like the basis of most machine learning, is that you would have an input of features, which is your F, and then you would combine all these with a weight vector, and you'd have your output Y. This W is what you're learning in your algorithm. And so this is kind of the foundational of what a neuron would be in the brain, and we'll kind of go back to that later. So most current algorithms are based on this linear classifier. Now, this feature extractor takes a lot of expertise depending on what domain you're in. So a lot of like the research in machine learning, or in these different domains, whether it was bioinformatics or computer vision, has it focused on what are the features we want. Even in audio, for example, that's like a big thing. But all those features are handcrafted. They're just kind of human-made, and because of what you've seen and what you've tried, you kind of guess and check and see what works, and then you kind of get this understanding of the problem, and we got more and more sophisticated features. For example, we have here, this is histogram of oriented gradients, and basically, if you guys remember your math, is basically you're just taking gradients across your image, and then at each pixel, it looks around and creates a histogram of those pixels and what bins they fall in. And HOG was such a big deal because it was one of the first person detectors that worked well enough to kind of talk about. SIP is another one. Textons these here are very similar to Gabor features, and the reason I put them in here is because you'll see that they look a little bit like the features you get from a deep network at a certain point. So kind of from the 90s to 2011, that's we had like a very specific framework of what we would do. And so kind of based on this early thing that we talked about, the perceptrons, in terms of the machines, you'd have your handcrafted features, send it into your classifier, which is supervised, and it would learn what the output would be, right? But then that kind of evolved, and the modern thing that we've kind of been spinning our wheels with for a really long time was that you would take these handcrafted features, you'd run an unsupervised algorithm, and the idea was that you would give it these features for a bunch of different objects, whether it was a tea kettle or a car or a bicycle. You kind of throw it into this space, and then it would cluster these features into groups. So hopefully you would hope that it was learning something meaningful, like all these features look like a wheel and all these features look like a window. You could put those together to kind of represent what a car would look like. And then you'd run that through your classifier. But what is revolutionary about the deep learning is that we no longer have to kind of go in and manually create these features. The idea is that it'll learn this representation, so kind of this hierarchical representation of the features. And I'll kind of show on the next slide what that means. But the cool thing here is that the orange, I was kind of showing off that you have learning at each of these phases. So not only, we were kind of learning here in the orange box in the classifier stage, you're doing it through the whole pipeline. So you're allowing the computer to learn what it needs to know to be able to see what that thing is, right? Because it's different, the way we look at stuff as humans is very different than what the computer looks at, right? Because we're not seeing everything as a bunch of numbers. And so this is allowing the computer to learn what it feels is best for classifying, let's say, a class. Not yet. Yeah, we'll talk about that a little bit later. But just a kind of, this is just kind of like a global understanding.
I mean, imagine you want to detect an apple. I mean, before, let's say 10 years ago, people would say, okay, I want to extract useful feature from an image. That would help me detect an apple. What feature would you say? Okay, probably I want some feature that would give me the shape, some information about the shape. So I would look for something that looks like a circle. And I may also extract some color features. But someone beforehand needs to think about all these things. Okay, what is good for me to use? And hopefully that's going to be good for the computer too. And then you would pass the feature extraction. And then after that, you have to come up with this sophisticated machine learning techniques that will take those features and classify them into apple versus non-apple. But what's beautiful about deep learning is that you don't have to do any of these things. You give it like a bunch of apple images and a bunch of non-apple images. And you just fit it into the network and it's going to do everything for you. It's going to learn what's useful, what I should extract out of this image in order to help me to separate these two into two different groups. So that's like the whole point behind this.
Because, and like he said, like the important thing is that it's what's useful to itself. Because, you know, we spend all this time kind of, oh, let's solve the color problem, right? And that in itself was a hard problem, and researchers spent like decades trying to like be able to give it an image and it tell me what's the predominant color in here. But we all know that, you know, each camera is different, and then you have to do all this calibration, and so, you know, it became this big problem that you couldn't, you know, an endless loop of never ending, and then you just give it a bunch of images and that's it. So what does this hierarchy of abstraction of representations mean? Is let's say I'm gonna show you in terms of a face image. So imagine you have a picture with a bunch of pixels. At the first, you know, the lowest level, you might want to try to find edges on the face, right? Like you'll see, and then you know that these edges are the edges of this face. So those are only going to be like this, and then the ones on the nose are going to be straight up and down, unless you broke it. And but the next part is you're going to look at the parts of the face, right? So you might have an eye, a nose, a nostril, and then you're going to look at kind of groups of those parts. So as you move through your network, you're getting closer and closer to what a face looks like, right? But at each level, you're learning parts of what make up that face. And then hopefully at the end, you'd be able to do that really well.
Each of these filters, like for example, if you have the first layer, this is, let's say, the first layer of the network. Even each of these features means something. For example, this filter here is going to help you detect all the vertical edges. This one is going to help you detect all the horizontal edges. And this is like going to help you detect all the 45 angle edges. So each of these filters are actually designed by the neural network to help you detect something useful about it. Even you won't be able to see it, but they're still very good.
And the kind of the ironic thing about this is that these are all things that computer vision scientists were doing kind of individually. So they would try to use edges for this, and then they might do like a part model, or even these object models here. You know, I remember even like reading papers from the 80s that they were doing kind of these filters that would try to match a face to this filter, right? And these are all things that people were doing individually, but the neural network actually can take it and glue it all together in a way that it works.
In this, in the colors here, this is not actually talking about like the colors of the image, right? It's talking about like the white is like strongly, these are similar, and black is like opposite of that, or this,
yeah.
These are,
yeah, like because it's like when you look at the edges, for example, here it's like a derivative. So when you're trying to find an edge, you're trying to find a strong derivative, and so here's like finding, you know, where the numbers change drastically across.
Look at this. Each of these squares has like 10 by 10 matrix. The whiter, the higher the number in that matrix, and you basically convolve this matrix with your image. I don't know that word.
Yeah. So you're gonna take the image, this little filter, and you run it across the image. So you're just sliding it across the image, right? And you're taking all the pixel values, multiplying it by these numbers that are in here. So imagine you'd have like, for an edge, like a strong edge, like a strong vertical edge, you'd have like all ones and all zeros. like side by side in a matrix, right? And you're like multiplying them. So you would find all the when you sum. So it's the math's a little more complicated, but when you sum all those pixels together, you're gonna find the strong edges, right?
We have examples.
And you'll have more examples. But the idea is that when you run these across the image, you'd find all of the places where there's a line, right? Like up and down line with, for example, that one. And then you could do these in a bunch of directions. And then for a specific object, you might find that you only need the vertical ones, right? So then it wouldn't even look at the other ones when it's trying to classify a specific object. So this hierarchy can be applied to many different domains. So for image recognition, we go from pixels to edges, to textons, to motifs, to parts, to objects like we saw on the previous slide. But in text, you might go from characters to word groups, clauses, sentences, and the whole story. And actually, I remember reading an article in Engadget where the guy was just kind of playing around with deep learning, and he had fed it a bunch of Engadget articles. And so he just gave it a topic and a bunch of words, and then told the computer to write a story for him. And it outputted like an Engadget story. And like it wasn't a good story, but it was cool to look at, you know, and he only spent like maybe a week on it. So I imagine if you'd spend a little more time, you'd get a better output. And then in speech, you're gonna look at you might have an audio sample of a word, and you're gonna look at your spectral bands. You might get a sound, a phone, a phoneme, and then you finally get what the word is. Now, I'm gonna go over like a bunch of examples of things that we've been working on. For example, with deep learning, these are actually some of the outputs. This was some of the early work from, I think this is even back to like the 80s, 90s. Because there was a few people that stayed on working with deep learning through all that whole time. But what was the major breakthrough is that now we have the power, right? So we have all the GPU power, the computing power that we need to be able to do this. And then also we have the data, right? We have all the image data. When I look at the papers from the 80s, you might have had, you know, an image per each class, and that's kind of what the data that they were working with. Whereas now we're talking about having millions of examples per class that you want to, like, per object that you want to classify. So here we see, this is not only finding faces, right? So it detects multiple faces in an image, it also does your orientation. They've been able to push the boundaries on recognizing multiple objects. So there was a challenge that they had been running for years, right? And everybody had kind of been spinning their wheels, and we were getting like maybe 1 or 2% increases every year is what everybody was spending their time on. And then all of a sudden deep learning came out to the scenes, and there was like 10% jumps, and then just kept going up from there. So also, I remember when I first started in computer vision, this estimating the pose, like human pose is very difficult in an image. And I remember a guy, I'd seen the work he was doing, was like, you know, in order to get this data alone was hard, but then when he actually did it, you know, the pose, actually there was one paper that he used the pose, and because it was so hard to do this with the computer, he would do it manually, and then he had an algorithm that tell you what action was happening based on what the pose was. But he had that manual step because it was so hard. And that was like in 2007, and then now you have these algorithms that you just give it an image and it pops out. At the last conference we were there, and they were showing real time of this guy had a camera and it was doing it in real time, and you just move in front of the screen and it was tracking, and it was laying all the parts in real time. No matter how I moved, it was still following. It was actually pretty cool. Because for the longest time, anything that was computer vision related, being able to do it in real time, like that you'd be able to run a video through it and get the output instantaneously, was unheard of. I remember, I think it was around 2002, like the first thing, like somebody walked into one of these computer vision conferences, he set down his laptop with a little webcam, and he took a snapshot and was able to do face detection on that image, like during the talk. And that was like a big deal, because nobody would dare walk in and try to do something live because it just didn't work. We have image captioning, so it's able to take an image and not only tell you what's in the image, but it can kind of make a comprehensible sentence about what's in the image. And we were actually at the big major conference, Computer Vision, this summer, and this is a video that they showed from Mobileye. And the CEO was showing this video, and if you don't know, Mobileye was previously the computer vision engine that Tesla was using for the autonomous stuff. And the cool thing that I thought about this video is that you can see that's labeling where the paths are that you can actually drive on, and it works in both clear and like in the snowy, really crappy situation in rain. But also, if you look at these borders here, they're putting slashes for raised borders, and then here these are actually not raised borders. So it actually, the neural network can distinguish between something that has like a gutter and something that doesn't. So I thought that was really cool.
The reason I was talking about labeled data, Mobileye mentioned their CTO that they had 800 people just annotating data. Like you can imagine like how much labeled data is being used to actually train these systems that are actually used in an actual self-driving car.
And when they started, they had barely any, but because Tesla started to collect all that data, they were able to just make it better and better. And so I imagine they had to hire more and more people. Probably one of the worst jobs ever, but it's helping mankind, I guess. So Nvidia just announced this year was you have on this board you have 12 CPU cores, but the awesome thing is that there's also their modern architecture GPU. That's the same one that's running in their Titan X, which is their top of the line for video gaming. But the one on here runs at 8 teraflops, and the one that runs in your desktop runs at 11 teraflops. So like the gap between what we can put in a mobile low power system is that gap is shortening dramatically. This thing can process multiple camera feeds and do it in real time. And CEO of Nvidia actually showed this video. And you can see that it's detecting multiple cars, people. And on the next one, it's actually showing the segmentation. So it's finding the signs, which is those yellow, people in green, and then it's actually drivable region being the purple area.
This is what's being used in self-driving cars.
Yeah.
These days, like Uber.
Yeah, Tesla also released a video, I think 2 months ago, of a similar output like this. And then in image recognition, it's very similar to what we're seeing there, but given this image, it's able to find all the people and the frisbee, and not only do that, but it also is able to segment it.
It was very difficult for me to see that person.
Yeah, the far left.
And
And
look like a person.
when I say segment, it's that it's able to like find the boundaries of the object that it found. So there's different things that you can do, like one algorithm might just put a box here and say this is a person. And then the next step up is more difficult, is to actually put where the boundary is of that person. Even though this is just a blob, but you can see this with cars, people. Here you'll see it with people, the cell phones, the laptop. It got just the screen. For all it knew, that could have been just a TV. Here we get all the people in the stands down here. Baseball players. Here, it's able to look at this food and find that you have carrots, your broccoli.
Actually, there's an app that you can take a picture of your dish and it tells you how much calories you can actually eat. And what's using underlying algorithm is basically segmenting the object, basically estimating the amount of the object in your brain. It tells you how much calories the food has.
So there's a few of those. There's one on Shark Tank. I don't know if you guys saw it. That it was like the guy had, in order for his to work, you had to buy their plate. So like they were kind of making fun because you imagine you have to go like to your restaurant and you have to take your plate. I got to use my own plate. But counting sheep. If you look at this image, it's like really hard to tell how many sheep there are here because they kind of just blend all together, and this algorithm can actually separate them.
This was a dream for computer vision, basically count the number of sheep in this image. And when deep learning came out, actually
And then finally, I kind of put this slide in because I just found this recently, but when I was looking at this deep learning thing, like, they tell you that it looks like a function, right? And so when you're reading the books, all they tell you is this function, right? And so it's either going to be a step function or a logistic function, which you'll see on the next slide. But I was like, what does this have to do with the brain, right? Like, what does it have to do? And so the idea is that you'd have your neuron would be receiving all these inputs, right? So this your axis, like we saw on the earlier slides, and then it fuses that within the neuron and is able to output your final thing. And so I just liked this idea of like the overlay of how they're related. And he'll be kind of talking a little bit more of what the pieces of this mean.
Cool. I mean, we're going to get into some more detail about this whole thing that we talked about. It's like confusing, just ask questions. I'm going to try to keep it very high level. So the simplest neural network is basically what you can see here, which is also referred to as logistic regression. You have one single neuron, which is this, and you have an input data, which is defined by X, and your input is basically only 3 values. So you can think of any input data which has only 3 numbers. And they're being fed into one neuron, and you're going to get an output from it. So the goal in this machine learning task is to learn the parameters of this neuron, which are theta 1, theta 2, and theta 3. So basically, you want to learn the vector of theta, and that vector is being multiplied by the input X, is being passed through a nonlinear function sigma, and you're going to get an output, which is defined by H. So you can see the visualization here. So this is the most simple neural network that you will ever see.
And just to be clear, that these values, like when we say the values that are being inputted, for us they're going to be pixels, but for other problems it might be just to simplify that you want to be able to predict the price of a house, for example. So you have like the location and the time of the year that it was sold and some other value, how many rooms the house has. And then your output people have something.
Yeah, if you have like a 10 by 10 pic image, you're going to have 100 pixel values as input. And you're going to have one neuron, you have one nonlinear function, and the nonlinear function has been defined here, which is nothing but a sigma function, which takes the output of here, passing through the sigma function to get the final value. And the final value could be, as Nvidia gave an example, the price of the house. If you put a series of neurons next to each other, you're going to have like a neural network. So it's called a network because you have multiple of those. Here you can see a 3-layer neural network. You have the input layer, you have 2 other layers which are referred to as hidden layers. So anywhere you see what's a hidden layer, any layer other than input is called hidden layer. And your goal is to predict an output. And this is a network with 4-layer and 2 outputs. Basically, let's say you are doing a classification task, you have apple versus non-apple, you input an apple image, you want to learn a bunch of parameters, okay, which is like a matrix of parameters, and an output, you want to output whether how much it is an apple and how much it is not an apple. The probability of that image contain an apple and the probability of the image not contain an apple.
Does each neuron in a single layer look for the same thing?
No. But each neuron has its corresponding parameters. And those parameters are basically referred to one of those filters that we were showing before. Let's say the edges. Each of them is going to look similar, not different from the other. So what each neuron is going to learn is going to be different from the other. So it's going to be like a neuron of your brain. Each of them activate when there's something in it. Okay. So yeah. So as we mentioned, given a network architecture, here you can see a network architecture, very simple one with 3 layers only, and given a bunch of training data, we are defining the training data as the top of here, x1, y1, which is x1 is your first training data, which would be your first image, and y is the label of that image, depending on your task, whether you want to detect a gender, you say whether it's a male or female, so y is a 0, 1, and x is your image. You have a bunch of these training images. And your task is to predict the labels such that it will match your labels in the training data. So let's say you fit a female image into the network. Let's say a photo of a person which is female, and you want the output to match the label of the image. Let's say the female label is 1, and you want to have 1 here and 0 here. And if you input a male image, you want to have a 1 here and a 0. Okay, so you want to learn those parameters such that the output matches the label of the image during training. And we're going to see how this is being done, and this is being done through an algorithm called backpropagation. And this is like the whole magic happens through backpropagation. So you feed it a bunch of images with a bunch of labels. How neural network is going to learn what's good, what's bad, how to adjust the parameters. So in order to make it simple, we'll try to come up with a simple example. Let's say you have your training data has only 3 values. So here I'm showing only 4 of the training data, and each training data has 3 values. So these 3 values could correspond to anything. Let's say, I don't know, you have grades. Let's say you have your grades and you want to say whether the person is going to pass this course or not going to pass this course. So here we have 3 values. Let's say for the first training data, 3 values, for the second training data, and the labels are 0 and 1. So these 3 are the input data. You have 1 hidden layer and you have the output. So what's going to happen during training is that first you randomly initialize these variables here. Okay? So each of these lines will correspond to 1 variable, like 1 parameter that you're trying to adjust. But in the beginning, you don't know what they are, so you randomly assign the value, or you set them to 0. You input the first training data, and you pass it through the weight. Basically, you multiply the input data with the weight, and you get an output. So you get 0.8. Then you look at the label of that training data, which was 0, and you compare it with the predicted label. So you say, okay, oops, I predicted 0.8, while I should have predicted 0. So there's 0.8 error. So what backprop is going to do is going to basically take the gradient with respect to the parameters and backpropagate the gradient through the network. And basically what's going to do in high level, when you do backpropagation, you're going to adjust the weight a little bit based on that 1 training sample. You said, okay, I saw I had 0.8 error, so that means I have to make adjustment to the weights, which is done through backpropagation. It's not going into details. So you change them slightly. Then you go to the next training sample. So you randomly select another sample from the training data, and now you pass it through the network. And you see you get a prediction which has less error compared to the previous one. So the more adjustment you make through the learning, this error becomes less and less. So you after you do this like millions of times, probably going over hundreds of thousands of training data, your network is going to keep adjusting those weights until the error is going to be very close to 0. That's how the magic happens. So let's say you want to detect the pose in an image. You have, let's say, 10,000 images of people with their pose locations annotated. So your input is going to be those images, basically the pixel values, and the output is going to be the joint locations. So this algorithm is going to input the first image, and get the joint values. You're going to compute the error. You're going to do backprop. You're going to make adjustment, and then you're going to do that multiple times until your error is 0. And when we talk about those libraries, basically you're going to see that the only thing you need to know is basically you do this through 5-6 lines of Python code. It's nothing more than that. There's like a ton of libraries out there that basically you don't have to know about backpropagation. Let's say you come up with your own algorithm. You want to take nudity in an image. You have to have the data and the labels. You can just pass it to 5 lines of Python code and it does everything. And we also talked about unsupervised learning and like what if we don't have labels and how people are going to train network when there is no label. I mean, this is probably something that you won't face with very soon in the future, but it's good to know what is the objective of the network when you don't have labels. What is the network trying to learn when there's no label? So in most of those cases, what people try to do is that they're going to try to design a network that's going to reconstruct the input image. Basically, you're going to input an image, you're going to get a prediction, and you want the prediction to be equal to the input data. So basically, you input a cat image, you're going to multiply with a bunch of parameters, and the goal is going to be to reconstruct the input at the output of the network. So if you kind of like just come up with a question, what if I don't have labels? How does this unsupervised learning work? This is mostly the objective that they're trying to solve through backpropagation. Okay, Now let's get into convolutional neural networks, which is basically the backbone to most of these applications that we talked about, which is nothing but what we just talked about. There's a few more changes that you need to know. Let's say we have a 200 by 200 image, okay? So we are not talking about 3 numbers anymore. We are talking about 200 by 200 image, which has like 40,000 pixels, 40,000 pixel values. Let's say if your first layer also has 400,000 hidden units. So how many parameters do you need to store in memory? You need to store 16 billion parameters. So this is like impossible to do that when you are talking about like big images and like big data. So having a connection for every pixel, every input data is impossible. So here is where the idea of convolution is coming to play. And what they are saying is that you don't have to have one parameter for every single input data you have. Let's cluster them together, put them together, consider a 10 by 10 unit, and just like share the parameters across the image. So basically, each of these neurons are connected to a local area in an image instead of the entire image. Here, if you can see, one neuron is connected to all the other pixels. Like this was what we saw in previous slides. But convolution networks, CNN, what CNN is saying, connect each neuron only to a local area in the previous image. And this neuron is also connected to a 10 by 10 pixel in the image. And these parameters are all shared across all the neurons. So if it's connected to a 10 by 10 region, you're only learning 100 parameters. Okay? So you don't have to have like too many parameters. So you reduce the number of parameters drastically. And why this is going to work? Because the pixel values, especially when working with images, that the pixel values are highly correlated, especially the ones that are very close to each other. You don't have to learn a parameter for each pixel separately. You can use that information and the correlation between pixels to share the parameters across different nodes. And what's going to happen is that in the case of convolution CNNs, if you have 400,000 hidden units and you only are looking into a 10 by 10 area, basically you're going to have 1,000 parameters. Yeah, this is going to be 100 parameters. And this is like the formula for convolution, how to compute the convolution. So each of these neurons are connected to a local region in an image. And this local region is, let's say, a 10 by 10 image. And the parameters are shared. So imagine you have a 10 by 10 filter, and these black neurons correspond to one of the filters. And you not only want to have one, but you also want to have like many more. For example, in a convolution neural network, you don't learn one filter. You may learn like tens of those filters, or like hundreds of those filters. As we showed you in one of the slides, like those edges that we were trying to learn, each of those correspond to one of the filters, let's say 10 by 10 filter. And you learn many of them. And when you convolve each of those filters with the input image, you're going to get a response. And that response is called the feature. So let's say in the first layer, you're going to learn 10 by 10 filters. And you're going to convolve those filters with the image, which is nothing but multiplication, this operation here. You're going to convolve them by the image, and you're going to get one response. And you're going to get, if you have 10 filters, you're going to get 10 responses back. To make it easy to understand, let's say this is the operation that's being done. So the convolution filter that we have is this yellow filter that is being passed. So you can see the numbers in that filter that are binary, 1, 0, 1, 0, 1, 0, 1, 0, 1. So this is the filter you have. You move it along the image, you multiply the yellow values with the green one, you sum it up, and you put it in the corresponding location here. You see when it goes on the top, you do the operation, you put the numbers. So this is called convolution, very simple. And you can very efficiently implement this in GPU. That's why like you can process millions of images very quickly in GPUs, and why GPUs are very important. Because it makes the process of convolution super fast. Is this clear? Yeah. Sorry, I didn't get the question.
Oh, so what happens if
You mean if they're sharing regions, or?
well, yeah, like if you have images that are
mean like if you like grab the 10 by 10 over here and the 10 by 10 over here, how are they still related even though they're in different nodes?
See, all the information for that 3 by 3 location on the top left is going to be stored in this pixel. The one next to it is going to be stored in this pixel. So, and what you can see is that you're missing some border information because the convolve feature is smaller than the input. Okay, we can talk about it. So to give you one example, like we showed you some of those filters in the beginning. Let's say you want to convolve this image with this filter here. This is the output that you're going to get. So let's say the neural network has learned a filter that looks like this. But when you convolve this with the input image, you're going to look at this. So you see that neural network has been trying to learn this filter so that it can get the edges out of the image. So probably neural net has thought that I want to learn about the edges. And through the training data, it has learned that these should be the filters, the parameters for one of the filters that it has to learn. Okay? So if you convolve this, do the same operation that we showed in the previous slide, on that image, this is the output that you're getting. So depending on what the filter is, you're going to learn different. So your question was that, let's say you only have ones here and you have zeros elsewhere, like one of that filter with vertical white bar in the middle. So what that filter is going to do is going to detect all the vertical edges in the image for you, if you convolve it across the image. Okay, we talked about convolution. One more thing that you need to know while designing a neural network is the concept of pooling. So in order to reduce the parameters, because neural network has different layers, we're going to show you what this means. And as you go through layers, you probably need to add some pooling layer. A pooling layer is nothing but just it takes the output of the first layer and it does the pooling by, for example, looking at a local region and does some operation on that local region. Here we are doing a max pooling on a 2 by 2 region. It looks at the red region, it takes the maximum value and it put it here. Look at the green region, take the maximum value and put it here. So this operation has been called pooling. As normally you use it to downsample the image and make it small to reduce the number of parameters and flops that you need to do during training. You can do average, you can do all sorts of fancy things, but the most popular one that you may probably use is max pooling, average pooling. Probably the last thing you need to know before start designing your own neural network is the nonlinear activation. I'm just going to give you a motivation why this is important. If you don't use nonlinearity during neural network, if you remember the logistic regression I showed you, you multiply the parameter theta with x and you pass it through a sigmoid function. That sigmoid was your nonlinearity. But why do you do that? Why is it important? Let's say you want to cluster the orange points from the yellow ones. If you don't use nonlinearity, neural network at its best is going to learn a linear classifier, basically just a line. Wherever you put the line, you won't be able to classify this data perfectly. So what you need to do is that you need to use a nonlinear classifier that after several iterations of learning, it's going to try to adjust the line such that, to adjust the parameters such that this is going to turn into a nonlinear classifier that classifies. Let's say in the beginning of your classification of learning, if you set the weight to be random, you're going to get a classifier like this. Basically, it's going to have a lot of it. But as you go through learning, you look at one sample. Let's say you're looking at the sample that I'm showing with red borders. This has an error. You're going to try to fix it. You look at another sample, you fix the error one by one, and at the end you get a perfect classifier that can classify the data like this. And this has been done by just a simple sigmoid function, nothing too fancy. Okay? So nonlinearity is very important. And the three most popular nonlinear functions that are used in deep learning and neural network are these three: sigmoid, tangent hyperbolic, and relative. And the most important one that you will see probably everywhere is the last one, relative, which is probably the most simple one. And it's doing nothing but just letting the positive number to pass through the way they are, and just setting all the negative number to 0. Okay? So if the output of your convolution has any negative number into it, when you pass it through ReLU, it's going to set them all to 0. And it's going to pass through any positive. So this was probably the most important before ReLU was found. And the reason people prefer ReLU is that it's going to add, first it's going to add sparsity, which means that you're going to set a lot of negative values to 0. It's going to make the network converge faster and the back propagation to converge faster because it adds sparsity. And the other important reason is that it basically eliminates the effect of vanishing, something called vanishing gradient. So to explain it in a simple word is that in sigmoid, any number, let's say any number greater than 6 is more or less is going to be mapped to 1, okay? And let's say you have number 100 and 101 or 102. So they are very two close number after mapping to 1. When you take the gradient, that's going to be almost 0. There's nothing to take the gradient. So the gradient is going to vanish if you have a very large number. So in order to avoid that, people have found that ReLU is more important. Is probably the solution. So vanishing gradient and sparsity are the main two reasons that people prefer to use ReLU over the theory. So Enrique talked about ImageNet challenge, that people for years has been trying to classify 1,000 classes. In ImageNet you have 1,000 categories, and people were trying to design features that best help them to classify these 1,000 categories. And for years, people were trying to do sophisticated things to get 1 or 2% improvement. But in 2011, Alex Krzyzewski, he designed this network, which is called AlexNet. And he showed that he was able to get about 15% boost in accuracy by just using this network. But the challenge at that time was how to implement it in CUDA. So he had a whole bunch of like C++ and CUDA code that was implementing nothing but a technology that was developed 20 years ago, but in a very efficient manner. And he showed that using a K40 Nvidia GPU, you can process 40 million images a day for your training. So ImageNet has about 1 million images, and you need to maybe train your network for 100 iterations. It means you have to go through each million images 100 times. So you have to process 100 million images. So if you don't have a powerful GPU, or if you don't have a powerful technique to implement it in your GPU, using your GPU, then you're going to be spending days or weeks to train your network, which probably you don't want. And this network is very simple, just based on the techniques that we talked about. The first layer of the network takes an input image. The input image is 224 by 224. It resizes all the images to 224 by 224, and it has the depth is 3, which means it's an RGB image. It's like RGB. What it's learning is learning 96 filters of 11 by 11. So it's learning 96 filters that they're very tiny, 11 by 11, and each of them are probably going to look like one of the edges that Enrique showed you in one of the slides. Okay? So when you apply each of those 11 by 11 to this input data, you're going to get a response. You have 96 of those filters, so you're going to get 96 responses back. Okay, that's what it means. Depth is 96 because you have 96 of those 11 by 11 filters. Then you have a max pooling. So the size has been reduced from 55 to 55 to 27 by 27. So whenever you see a max pooling, you definitely are going to have it reduced in size. And then it's going to learn 256 filters of 5 by 5 sizes. Okay? And there's no magic. You keep doing that, and you have some fully connected layers. These are the fully connected neural networks that we showed you in the beginning. But since the image is being downsampled by a lot, you see the input gauge is only 13 by 13. So you can afford to have one of those fully connected networks that we showed here. These are called fully connected networks, that everything is connected to everything in the previous layer. But since he's downsampled the image a couple of times, the image when he was doing fully connected layers was only 13 by 13. See the size at 13 by 13? If we put two fully connected 4096 neurons, and at the end you have 1,000 outputs. Let's say if you input an Apple image, you only activate the label for Apple. All the other labels are 0. If you input a dog image, you have 1 for a corresponding dog label, and everything else is 0. So it's very simple. There is no like anything like sophisticated. Okay, this is like probably, I would say, this is a very hard question yet to answer. Like we asked him in one of the talks that he gave, why not like putting 2 more layers? Why not trying like 4 layers only? He said we tried all of it, it didn't work. This worked better. Yeah, I mean, and it's all about accuracy. If you get like 1 or 2 more % better, I mean, they would work, but I mean, this one was like probably 0.5% better. So they ended up like going with this one. And you can try any combination. Some of them is just luck. So when you are like probably want to implement your first network, you say, okay, what should I put? If you ask me, I say, I don't know. Just try it. Start with AlexNet. Start with one of the famous networks that people have already tried, and it's been proven that it's going to work mostly for most applications. But you probably need to make adjustment to it as you, depending on your application, your image size, your feature size. You may want to use audio, you may want to use text data. So you may want to modify this a little.
AlexNet's actually freely available online and just for people to play with, and the training network. So you've got the network and the weights. So like every parameter that he's been talking about learning, they've already trained it, so you can download it. So you could just give it an image and see what the output is, and just kind of try it out.
If those 1,000 classes that AlexNet is really training for is of your interest, again, 5-6 lines of Python code, you can input an image, feed it to the network, and get those labels.
Are those network filters that I set, or are they?
No. Those filters, in the beginning of training, you set them randomly. But as you go through training, with those back propagation that I was talking about, you pass the first image, you compute the error, you do back prop, you adjust the weights. So you have to do it over and do it over and over. Like probably after like 1 million iteration or 2 million iteration, your network is going to converge, which means that the error at the end is not going to change much. So this is the time that you need to stop your training.
Will they drop? Some filters drop when they go to 0?
Or just some of them might be 0, some of them might be 1. I mean, they can be any number. So those filters that we showed you in the beginning, okay, here's an example here actually. These are some of the filters. You see this black bars, these mean they are 0. This white means that they are 1. So, I mean, they could be anyone. Okay. So, okay, this is, and nowadays the networks that are winning, basically the winner networks of ImageNet Challenge are much deeper than AlexNet. This is called BGG network, was designed by Oxford people. Again, when I say it was designed, you like don't see anything like different in here. You already know about convolution, you already know about max pooling, you already know about fully connected layers, you know everything. And this is just, if you want to use a fully connected layer, you just put 1 line of Python code in your script. And just put a fully connected layers and you could set the parameters. I'm going to show you how to do that. This is it. This works. So I don't know why, but this worked.
I think at least like since that first 2011 paper, 95% of the papers don't contribute anything to the science of it, right? Like it's mostly let's try this and this and that, and then let's see if it works for this problem. So they might change the problem, but the networks are very similar. And then, but then that other 5% will actually go in and be like, this layer, I'm gonna invent this new layer.
Yeah, but for probably, if you guys want a job, just learn the basics, try it, and a lot of companies just want you to do that. Yeah. I mean, they don't care about if you can design the next layer, the next different convolution layer, or next different pooling layers.
The researchers in there, you know,
they're so pissed off.
ivory towers, you know.
Don't wait. There are people who are gonna make.
There are people who are doing that, but for all intents and purposes, you want to know the basics and like you know your Legos, and then you go glue them together and make something that works.
So at SiteHound, a lot of things that we try to do is that we try to make these faster. We try to like design networks that are super fast, which you can run them on your cell phone, which you can like put it on TK1 chip. I mean, these are like a lot of things. There's a lot of things involved. Like even when you want to process one image through VGG network, just testing. You want to process one image and get the output. That's on a normal GPU. A normal GPU, I'll say.
Which one? Sorry, I was.
Yeah,
I was
let's
thinking of
say
something else.
on your laptop GPU, I mean, it's going to take about 2 seconds to process that. I mean, but you can't afford that. If you want to process it on a cell phone, you need to make adjustment. You probably need to reduce the number of layers. But as you reduce the number of layers, you notice that, okay, oh, the results, I mean, it's not working. So probably you need to do like more stuff to make change.
And like nowadays, like these competition winning methods, they actually will do like, they might train like 5, 6 different networks and then combine the results from all of them. So imagine you had like, if you had 2 seconds for each of those networks, it adds up and then before it, but it's real time to people in research, isn't real time to people, you know, in the real world.
This is the network that won the image challenge, I think, 2014 and 15. This is called GoogleNet. And the idea is that there was different loss function in this network. And they're like, this doesn't look like a sequential network as you can see on the top. And the most recent one, which is like state of the art, is called ResNet. This was the winner of ImageNet in 2016. And this was designed by folks in Microsoft Research. Okay, now having an idea about this, how network, what network is and how to design a network, let's see how to do it. So we're going to go over 2 different libraries. One is Caffe, which is, I don't know if you guys have heard of it. This is one of the most popular libraries. And try to play around with it first. But if you guys are Python lover, the second one that we're going to talk about is purely Python. So this is like the backend is in, everything is in C++ or CUDA, but there are Python wrappers that you can use to get around if you don't know C++ or CUDA. So what you need to do before designing a network, first you need to prepare your data. Let's say whatever task you have, if your task is classifying gender of an image, basically you need 10,000 images of male and female and their labels, corresponding labels. So what I mean data, this is what I mean. If you want to classify audio, you need probably signal in whatever format you have. If you want to classify text, you need to just prepare your data. And Caffe requires 2 input formats. One is level DB and the other one is HDF5. When you prepare your data, the second one is you have to come up with your network definition. If you don't know where to start, you can always start with AlexNet. You can start with VGG, GoogleNet. They're online. You can get the architecture in Caffe, Keras, or Piano, TensorFlow, any libraries that you want to use. You most definitely are going to be able to find the architecture already written for you somewhere.
Caffe has the model suite. So you just go in and people contribute all kinds of models.
Then after that, you need to choose your parameters for optimization. We're going to talk about it. And then you just start the training. That's it. So how do you define a network in Caffe? I mean, what you need to do in Caffe, the network is defined in a format like this. Let's say you have a very, very simple network that takes the data. You have one convolution layer. And let's say you have the output. Your network consists of just one convolution layer. Your network definition is going to look something like this. Each layer has been defined by a few lines like that. You have the name of the layer. Here the layer name has been conv1. You have the type of the layer. It's either convolution, it's fully connected, which is inner product. You have the loss layer, you have the input layer. There are many, many layers that you can go to Caffe website to see what layers does it support. You define the bottom and top layer. Let's say this layer takes the data and the top layer is conv1. So where the input comes from, where the output goes to. Okay? And you define the convolution parameters, what the size of the convolution you want to be. Here the kernel size is 5. Basically it means it's going to learn 5 by 5 kernels. Okay? And it's going to learn 20 of those 5 by 5 kernels. Let's look at this example. So this first layer, what is the kernel size? 11 by 11. How many of them do you have? 96. So if you go here, this should be 11, and this should be 96. Okay? Sometimes you see a stride. Basically, it means where do you want to put the convolution layers. If you see this, set the stride to 1, it's going to basically go over every single pixel in your image. If you set the stride to 2, it's going to skip pixel like one after the other. It's not going to go over all pixels. And weight filter, this is how you want to initialize your filter. You can, if you don't set it, I think it's going to set all of them to 0. And there are different initialization techniques. You can set them to a Gaussian distribution, or you can use different techniques. Just check the website to see what's the difference. So once you know how a layer has been defined, your network is a series of these layers. You have the data layer, and you have a bunch of convolution layer, as you saw in AlexNet. And then you have your loss layer, and that's it. Your network definition is done. Okay? Yeah, you can see several architectures here. This is LeNet, which was the digit classifier. It was used in many ATMs in the 90s. This is the AlexNet architecture.
Net was released in the 80s, so like,
Yeah.
right? In the late 80s.
Yeah.
Early
Better,
90s, yeah, but,
and this was the simple logistic regression that we talked about that has just one layer and a sigmoid function. The next thing you need to do after you define your network is that you need to set your parameters. We didn't talk about the stochastic gradient descent that was used like during training. If someone is interested to us, we'll talk about it. But there are some parameters that's related to your stochastic gradient descent. You need the base learning rate, momentum, weight decay, maximum number of iteration, how many times you want to like go over each image and how many images you want to process. It all depends. And most of the time, these numbers don't change for a particular network. Okay, so if you go read a paper or if you read someone, this guy use these parameters, just stick with those if you're using the same network. That's most likely going to work for your case. Okay? And in Caffe, it's very simple to switch between CPU and GPU by just setting the solver mode here. If your laptop has a GPU, just set this to GPU. If it doesn't have a GPU, just set it to CPU. Okay? The second library I want to talk about is called Keras. Keras is a powerful, easy-to-use Python library, and it wraps around two different libraries. One is Theano, and the other one is TensorFlow. TensorFlow has been released by Google, and a lot of Google researchers use TensorFlow. And Theano is the Python library that supports GPU, and it's super fast. And that's why like Keras work on these two backends. Why I like Keras? Because you can define everything in a few lines of code in Python, and everyone loves code. So why not do everything? It's very great to start with. Caffe is kind of still like sophisticated in a sense, but in order to start with, I think Keras is one of the best libraries to start. For training data, I mentioned you need some data and labels. Let's say we call our input data with X and the labels with Y. So let's say all your data is stored in a text file or a CSV file. Okay, so in Python you can load the data, put it in data set, and our data has only 8 variables in it, 8 values, and the last column is our labels. So let's say you load your data in this manner. So you have a matrix X which contains all your data. It could be a lot of images, and you have labels. Then you define your network. I think when you look at this, you can easily tell what it is now. The network is a sequential network. You have to define that, which means that one layer comes after the other. We're going to put 3 layers here, and you can define the parameters of the layer along with the activations in just one line. You don't need like a couple lines of parameters in Caffe, such as you need it in Caffe. You can put it all in one line. You need here, what it's doing is that the output has 12 neurons. The input, as we saw, had 8 dimensions. This is the initialization of the weights, and the activation is ready. As I mentioned, this is the most popular. After that, we're going to put, again, another layer with 8 neurons, and the activation is ready. And the last layer is going to have just one number. Let's say if you want to classify male and female, just want to give you one probability. Let's say how likely that image is as a female. Okay, so you're going to have one neuron at the end, and you're going to use a sigmoid activation. Why? Because you want to get a probability as an output. Sigmoid is going to map everything between 0 to 1. So if you want to say how likely that image contains a female face, you would like to get a probability back. You don't want to get like any number like between minus infinity to plus infinity. You'd rather to get a probability. That's why you set a sigmoid. And you got to have two more steps. You're going to compile the model, and you're going to define your loss function here, how you want to compute the error at the end. Let's say we showed you an example, the error was just the difference between the label and the predicted value, but this error could be computed in a different manner. So that's what the loss function is going to do here. You can study that on your own, different loss functions, depending on your application that changes. And you're going to define your optimization method. This could be SGD, stochastic gradient descent, or Adam optimizer. Again, this is not something you really need to know what it is, just to get started. And then you just start the training. The training epoch is going to define, basically, this is going to define how many iterations you want to process all the images in your data. Let's say if you have 1,000 images in your training data, 150 epoch means that you're going to go over 150 times 1,000 times. So basically, you're going to go over all your images 150,000 times. Okay.
Does the order matter?
Does
the order matter?
You got to compile it before you start the training. And the batch sizes means like at every time, how many images do you want to process? The example that I showed you, at every time during training, we fed one image. But it's better to adjust the weights based on more than one image. And how many images you use during training really depends on your GPU memory. So if you have a Titan X at home with 12 gigs of memory, and you have a very small network, you may be able to process 1,000 images at a time. But if you have a very small GPU, you don't have the fashion to actually increase this number right now.
And the bigger you can get that number, I mean, eventually you kind of peak, but your convergence will be faster, so you'll be done quicker.
Yeah, and here you can see how it converges. You see this shows the number of epoch, and this shows the loss function. You see at the very last epoch, let's say when you reach toward the end of the optimization, the loss doesn't change much. But probably the loss in the beginning was very large, probably around 10, 9, 5, whatever. But as you go through different iterations, the loss decreases, and basically you know when to stop the optimization. Basically, you look at the loss function. Whenever it's not changing, you're going to stop the optimization. Okay. You can also compute the accuracy at the same time on a validation data. Let's say you have 1,000 images of male and female that you want to use during training, but at the same time you want to evaluate how well your classifier is doing. So you leave out, like, let's say 50 images just for validation. And after each epoch, you keep computing the accuracy on those 50 left out images. And this is what the accuracy is showing. At the end of the optimization, this is not going to change much. But in the beginning, probably it's around 50%, which is random. But as you go through optimization, this is going to increase, and hopefully it reaches to very high. There are some more libraries for deep learning. We talked about Caffe. You can look at Theano. Keras is based on Theano and TensorFlow. There's another one which is very, very popular. It's called Torch. Torch has been maintained by Facebook. Again, it's based on the language called Lua. I don't know if anyone knows about Lua. But again, Lua makes like the use of GPU very, very easy. That's why it's very popular for deep learning. Again, if you guys know Lua, you should probably stick with Torch. Everything again in Torch is also very similar to Keras. So you can define one layer with a line of code. The difference that is going to be Lua. Any questions?
So kind of wrap up, I wanted to give like a final kind of background of what we do at SiteHound, and you can see the logo there. But basically, the idea is that we're a platform for computer vision, and so we want to kind of make computer vision easy for developers. Well, you don't have So we have several products, and I just wanted to show you the cloud platform. So it's just a REST API, but the idea is that you just call our API, you get the output. But here you'll see that we have person detection, face detection, and with the faces you can get different information. So for example, we have age. This was just recently released, maybe a month or two ago, and this is like always expanding.
So here we have gender estimation.
Gender as well, the blue and the pink. And then we also have recognition of people. So here you'll see that it was this Vanity Fair sign. You get Tom Hanks, Brad Pitt, Tom Cruise, Harrison Ford, and you can train your own people. So the idea, so we have a celebrity recognizer, but you can also just train your own people. And so you just send up your images with a label, and then whenever you have that person come back, you can label new people. We also have authentication. So the idea is that is this person who they say they are, right? So like if you log into your laptop or phone or whatever, we have that available. And we have a lot of other things coming, like end of this, actually this week we have, we probably already announced that, right? Because that's this week it's coming out. So
A lot of cool things coming.
yeah, coming this week. So check the website like towards the end of this week, because there's a lot of new things coming out this week.
You don't want to go through the hassle of coding everything. You can just call our API in your application if you're thinking of any with just simple few lines of code.
Because you know we spend a lot of time getting these algorithms to be as accurate as possible. So for face recognition, it's solved, you know, here, and you can just use it. But if you have something completely different, then you go improve your own. Yeah, and then you can download the presentation. You can see that link, right? Uploaded it. There we came up. I want to make sure that it. Yeah, I'll make sure if this link doesn't work tonight, I will for you guys like right now immediately I will fix it tonight. But I uploaded it before we came over here. And it's free to have questions. I was thinking as we were talking, so I put these sources at the end. These last three are just the slides some of the slides that we borrowed from here. But the machine learning is fun. This guy wrote kind of a blog on Medium that gives you an example, like a step-by-step example on machine learning and deep learning. On like the first part is just machine learning in general. Then you jump into deep learning on the second part and the third part. And it's a very simple, like this is meant for people that have never done machine learning in their life and have no idea what's going on. And when I was looking at it, it was very useful. Like I liked reading it too because it's kind of to see it from a very, very high level, and it also gives you like step-by-step sample code on how to do these things, kind of similar to what he was doing, but even simpler. So I highly recommend going to look at that one. So any other questions you guys might have? Yes?
I'm just curious,
Overfitting happens if you, let's say, have a very large network and have very few training samples. So basically, it's going to overfit only to your training samples. You can't really generalize it to basically other samples that it hasn't seen during training. So anytime that you guys want to avoid overfitting, it's always good to have a left out data, some data that you're not using during training. As I made an example, you have like 1,000 training sample. Just don't use 50 of that 1,000, like 5%, 10%, 20% of your data. And as you're training your network, just test it on the data that the network hasn't seen during training. It's called a validation set. And if your accuracy is going up or it's like being reasonable, let's say sometimes you get a loss 0 and your accuracy is also like 50%. So in this case, you see an overfitting. Your loss is 0, your network is perfect, it's supposed to be perfect, but your accuracy is 0. So this happens, this is the overfitting. You don't want that to happen. That's why you always have left out data of validation, and you always test it on the validation set to make sure that your network is not overfitting.
And these algorithms, like the libraries, they have things that they're doing mathematically to kind of try to avoid. Like, what do you mean? Like for text recognition?
Yes.
So,
I mean, if you basically are thinking of predicting something that you have never seen during training, right? I'm trying to think of some work that people are doing on that. But I think from learning perspective, it's kind of very difficult to predict something that you've never seen. Especially, let's say, for classification, if you're trying to classify 1,000 objects, if you give it an object that you have never seen, what's going to happen is that the score for all those 1,000 objects is going to be very big. So, like for example, the celebrity recognition that we showed you in our demo, let's say we have trained it for thousands of people, but let's say you input someone, let's say in this room. You input it to the system, it's going to say unknown. Why? Because the score for all those known classes are low, so it says, okay, I don't know who that person is. But if you want to add that person, you can train it, you can give it training for that face, and it's going to be able to recognize. They actually have face recognition app on the phone that we can show you.
I'll go with questions. So Ashton, say you're doing this training and you end up with an accuracy of about 80%, you've converged and everything, and you decide that 80% isn't good enough for your application. What would be your next step here as to, would you, pick a different algorithm? Would you train, try to find more data to train? What would be your next step?
So you mentioned probably the first thing that we should do if you don't have enough training data is probably to add more training. The reason that your network is not able to classify the data in validation set is because the validation set is different from training set. Like, there's like more variation of the data that it hasn't seen. So one way is to add more training. The other way is that your network might be like too big. It might have like too many parameters that it can't actually adjust all of them. So you may want to like change your network architecture, or you would want to there are like network fewer parameters that actually work better. So there's a lot of things that people do, changing the architecture, adding more training data, changing the parameters of your network, and those could help.
What about with your evaluation data? Is there a certain size of evaluation data as compared with your training data that's considered optimal? Because you were mentioning, starting out with 1,000 pieces of training data and maybe using a subset of 10 for evaluation. That seems like pretty small subset to me.
I mean, that really depends on how important that test is for you. Let's say if you're talking to a customer, you say, okay, I've tested my algorithm on 50 images and it gives you 95%. They're gonna laugh at you. Okay, 50 images, seriously? I mean, it depends who you're talking to. If it's only for you, you just wanna see, you're just looking for a proof of concept, you don't really need like 10,000 validation images. 50 images is gonna tell you, okay, this is relatively good. But if you're like talking to a big player, I mean, you need to show, okay, my system works on millions of images with like 95% accuracy. Then they're gonna believe. So it's really subjective. But in terms of like how well, I mean, your algorithm is doing, the validation so it's not gonna affect it that much. So that was like the beauty of it. Like, look at this slide here. The backpropagation is gonna pick the weights itself. Okay, so You initialize it randomly. You compute the loss at the end, and then you do backpropagation. And we didn't cover backprop and how the backprop is computed. But that backpropagation is going to make small changes to the weight that you have initialized. And by the end of the optimization, those weights are going to completely change to something that you never expected. So those weights are being found automatically. What's that? No, it could be any number. Yeah, it could be any number. And it's being found automatically. Yeah. I mean, talking about pre-processing, that's actually a very important step, especially because it's very important that your network converges quickly. And in order for it to converge quickly, people have found that some pre-processing are essential. And one of those pre-processing is that you basically look at all of your samples. It's like the mean subtraction. You want to subtract the mean of your data from each training sample. Like if you have 1,000 training samples, you compute the mean value for every pixel, and before inputting that image into the deep network, you want to subtract that mean value. So you basically want to zero mean all your training. So there are several pre-processing that help you speed up the training. But overall, if you have enough training samples, those pre-processing are not going to make a huge difference in terms of the performance. But it's going to help you to converge quicker to your desired solution. Very good.
A lot of this is often used with like media stuff like sound or video. Is there any reason that you don't hear about it more for just like, I don't know, like rewriting pricing or something like that?
It's being used everywhere. I mean, it's being literally used everywhere. I mean, every day we see something that we could never have thought. I mean, people are using, you can use it for any classification. Machine learning has been previously used in like a lot of applications. Data scientists, statistics, everything.
I remember when I was finishing undergrad, Netflix released their challenge, so they gave a bunch of data, and then you could try to. We did it as like our senior software engineering project, and I bet you by now they're using deep learning. Okay? So you can see it there. So even things that we're interacting with every day, it's there.
I mean, you can come up with your own project. Let's say you think of something. I mean, you guys can Google us, email us if you have a cool idea you want to work on. We can always help you out to get started. If you think you can come up with the next data classification task that could be important, just shoot us an email. We can discuss it. If it's something that you need suggestion, we can always help you. Maybe we can do something.
Actually, and that's another good place to look is the Kaggle competitions. They're like almost all of the data-centered ones, they're using deep learning. So, like if you ever enter one of those, it's good to have that in your toolbox.
Yes. I would say you can use it, always stick with me. The reason is that most of those machine learning techniques, let's say gradient boosting, or like, let's say other classified like random forest or SVM, or other machine learning techniques, classified that people are using, they are dependent on the feature that you give them. They require an input data, which is some sort of feature from the end. And those features are always handcrafted. Most of the time,
really good feature.
You need to design a really good feature. And most of the time, I mean, those features are not going to be as good as the one that is being automatically discovered by neural networks. So I mean, you can even design like the same idea using a neural network. You can design SVM using a neural network. You can design something similar to random forest. So I would suggest if you know how to do it, just stick with it. And I think from this presentation, you should have a good idea of at least where to start and where to look for. So if you have the only time that probably you don't use neural network is that when you don't have it. you, let's say, if you want to classify two classes, you give me an example if you have something in your mind. I can tell you. Yeah, okay, let's say
You only have 10 images each, like the neural network's not really built around this feature.
what kind of boat it is. I mean, okay, so look at the SciTown website. I mean, we're gonna have like a very good example similar to that coming along soon. What kind of boat it is? I mean, yeah, I mean, if you have only like, yeah, if you want to say the type, then this is gonna be probably an easier task to do if you want to like recognize exactly. But if you want to come up with the model of the boat, then that's a much more difficult task. Yeah. If you want to do deep learning, you probably need a lot of images. If you can get like thousands of images of different boats, you want to stick with like, let's say, hog feature and SVM. What's that? Uh-huh.
To find what or not?
Yeah, if you would just want to say this is it or it's not, I mean, for deep learning, my experience shows that you need at least 3,000 to 4,000 images of each class. So even for a simple labeling task, the reason is that if you design a very simple network with like few layers, you're gonna have still about hundreds of thousands of parameters. You can't really learn those many parameters from like 50, 100. But if you stick with SVM, let's say I don't know if you guys have heard of support vector machine, maybe. You extract some hog features. Let's say you go back to those handcrafted features that we talked about here. Let's say you give it an image like this, which is, I don't know, 128 by 64, which is about, I don't know, 100,000 pixels in it. When you extract hog feature, the hog feature is going to have like 64 dimensions. It's going to be very, very compact representation of your image. And when you train the support vector machine, you're going to learn only 64 parameters. So for that 64 parameters, you don't need many images. But if you want to do this task with neural network, you're dealing with like millions of parameters. And you have no other option than gathering more. But guarantee that's going to. If you feed like hog SVM, like, I don't know, 10,000 images, probably you're going to get like 2% boost. But if you give it to neural network, you're going to get like 20%. And collecting data is very easy, by the way. I mean, you can find crawlers everywhere, crawl Google, different websites, and get data. Yeah, a lot of understanding of how a lot of people who doesn't have the machine learning knowledge, they look at these as black box. They say, okay, a lot of companies actually start doing machine learning without half the people. They just tell their engineers, okay, we want to do this, go figure it out. You got 1 week, 2 weeks. It's not impossible. You just kind of get lost where to start and which library to use. So that's like kind of becomes very complicated at some point. But I mean, as long as you know where to begin and you have the data, it's actually not very difficult to just get started.
Or you can do something like AlphaGo, where not even the developers know who made decisions.
SVM, yeah. This does the magic for you. Yeah.
We discussed a lot of classification applications for this. Is there a lot of tracking as well?
Oh, tracking. It's actually the problem with tracking is the temporal information. You need temporal information, and when it comes to temporal information, it becomes more sophisticated. You can't directly use CNNs, but there are tracking techniques that are using CNNs to extract useful feature to track. At SciTown, we do a lot of tracking, like that face detection that we saw. It on tracking. Track object. We have application that you can track object using drones, and the drone will follow the tracking papers that I have in mind that actually use CNN, they mostly use CNN to extract useful features from the target that they want to track and use those features to actually tell where the target is going. Instead of using HOG, they're going to use deep learning to extract the features.
And the bit of CNN that they use, is that still like real time, applicable on commercial grade?
Yeah. I mean, depending on how big your network is, I mean, you can always go with smaller networks, fewer parameters, that you can run real time on different devices. But again, the state-of-the-art techniques are the very deep networks. If you're going to go with shallow networks, you're going to lose accuracy. And how to keep that accuracy high is still like a very active area of research. Should be.
The other thing you see, Charlie, is it's straightforward once you start to design these. If you understand exact layers, to tell like if you start like becoming so optimal in one way to know what kind of layer you need to add, or and is that like the steady process? Like you know you need to change like how do you know if you like add more layers or change like where your loss functions are or what they are? Like,
I would say you need definitely you need a good understanding of each layer, what each layer does, and where to put each layer, like where to put the pooling, where to put the convolution layers, and most of it comes from after you understand all the concept. Let's say this is like 30% of it. The other 70% mostly comes from the experience. You just need to start play with it, to see how it like affects the performance, and then you can get a good idea of where to start from. And again, just look up examples of how to compute the number of parameters in the network. And depending on your application and the number of training data you have, you may want to have a network with a certain number of parameters, and that affects your design. So when you know, okay, I want a network that has 1 million parameters. Why? Because let's say each parameter takes 4 bytes of your memory. 1 million times 4 is going to be about 4 meg, and you only have 4 meg space. And you want your network to have 1 million parameters, so you have to design it such that you stick with the law. So you're restricted by the filter size, number of filters. Did you work with Oliver? Not really about that.
Okay, well, if that's all the questions, please thank our speakers, and this has been a really good talk that everybody seems engaged with. So thank you, Action and Nvidia.
And I could have put a small, little capstone on this. David, I don't know if anyone who came out to the .NET meetup about 2 months ago, David Crook was in Orlando. He is a machine learning contractor consultant with Microsoft, who talked about the democratization of machine learning. What these guys are doing here are, if you want to do something like a self-driving car, there's a lot of work on your part because it's still a lot of research and a lot of development. But there are certain things that, as developers, it's really easy to do, like text-to-speech, speech-to-text, character, facial, and object recognition. And there are web APIs that you can do that. You can use those. So you can build an application, you can send it off to a company like these guys have, and they'll send you back all of the pertinent information. So the mobile app says, oh, there's broccoli in your dish. So it's really easy to get started with a lot of these complex tools.
So our idea is that not necessarily going to come up with all of the next big things, but we can power the next big things.
You have an application which you want to recognize celebrities in it, right? Mobile app, process language, site. Do a lot of cool stuff.
Guys like these are doing a lot of work to keep us from doing a lot of work. It's really nice. Just before we go, I'll have a shameless plug. We would like to do a bit of a feedback session with you guys, if anyone wants to stay around. But starting next year, I'm also just starting up the revamped Orlando Machine Learning and Data Science group. So if you really like this talk,
and have been hankering for some more topics like this, definitely come out. Our first one is going to be, we are the second Tuesday of the month here in the Iron Yard, and we'll see how long we can stay in the space. Our first one is how to make effective data visualizations, and our goal is to make it more of a workshop-oriented meetup. At least half of them are going to be workshops, and half of them will be full-fledged talks like this. So coming out, that's the end of the meetup. Stay around if give us some feedback. I don't remember the exact date. It's the second Tuesday of January.
Also, if you want to